Thank you. First, let me say thank you to the organizers for inviting us and also the sponsors for making this opportunity available to hear a little bit of chemistry. And I heard about engineering just now, and we are in the area of biorenewable hydrogen, in that we are trying to utilize and make hydrogen from biorenewable materials, aka we're using plant material to do this. Now, we've heard about the climate crisis, and everybody has that information in their heads, but what we have been considering is about the materials crisis. When we solve the energy problem with the blue hydrogen, etc., what happens to the materials, the clothes we wear, what happens to our plastics that we need to use? We actually do need some carbon materials. And so, let's go. It's not moving. So I'm going to introduce my two students. It should be moving. Yep. So we are into the biorefinery concept, which means that in a traditional refinery, we make lots of materials, and we can actually produce most of those materials from existing biomass. So that's your grass outside, your sugar cane stuff you throw away, the corn you throw away, etc. That's what we're doing. And this is so that we can have carbon-based chemicals and commodities. And in the roadmap that we're moving to using hydrogen for electricity generation and of course electric vehicles, etc. In that roadmap, there'll be many places where they will still need liquid carbon fuels, possibly, right? And so this is sort of a dual exercise. One of the issues with that is that the biomass molecules, if you, I don't know if you can see clearly at the top, they have a lot of oxygen in there. And to get rid of that, we need hydrogen. And so the presentations today will talk about sort of connecting the issue of where do we get that hydrogen from without having to do sort of the things that people have been talking about, make hydrogen separately, then transport it, store it, and use it. We want to do that all in a one-pot process. We want to do that in one process to increase the sustainability. So I'll hand you over first to Freida, who'll talk about her work, and then Ahmad.
Hello, everyone. My name is Freida, and one of the major focuses of my work is using thermal energy and catalysis to convert biomass derived or waste derived molecules into valuable chemicals and fuel precursors. One of these important molecules that I'm focusing on is glycerol, which is a byproduct of the biodiesel industry, and it's actually 10% of the total output of the biodiesel industry. However, the glycerol that we obtain is unwanted and unused. So our focus is to take this glycerol and to do different types of chemistries on it to make value-added products. My specific focus is on doing aqueous phase reforming on glycerol to produce hydrogen and carbon dioxide, which is a major point of the symposium. Another bio molecule that I am focusing on is levulinic acid, which is derived from the lignocellulosic part of biomass, so the non-edible part of biomass. And levulinic acid can also be converted to value-added products using different types of chemistry such as oxidation and hydrogenation. My focus is on the hydrogenation of levulinic acid to produce gamma valerolactone, which is a green fuel blender, and green solvent, and it's also a very safe chemical to handle and store and transport. We can actually couple these two processes, so the aqueous phase reforming or APR of glycerol with the hydrogenation of levulinic acid to use the hydrogen produced in situ. And this actually eliminates problems associated with the transportation and storage of the hydrogen that is being produced. Um, our goals is to do this in a one-pot process with low metal loaded catalysts and small amounts of catalysts. And our target is to use green solvents such as water. Just to quickly touch on some of the work I've been doing in my PhD, I have already successfully done APR on glycerol. And if we look at the first plot, what we can see is the blue line is actually the production of hydrogen as time goes on from glycerol. The pink line is another product that is produced in the same pot, which is 1,2-propanediol. 1,2-propanediol is produced when glycerol undergoes hydrogenolysis. So what's actually happening in this system is that glycerol is undergoing APR, producing hydrogen, and then using the hydrogen to upgrade itself into another value-added chemical, which is 1,2-propanediol, thus self-upgrading. And the key takeaway here is that the hydrogen production is much higher than that of the 1,2-propanediol. And since the hydrogen is in the gas phase, we can easily separate the products. Finally, the last plot shows the coupling of the levulinic acid hydrogenation with in situ hydrogen production. And the key takeaway here is that glycerol could actually comparatively donate hydrogen to upgrade levulinic acid to gamma valerolactone, which is our green solvent and green fuel precursor. And it performs just as well as some of the other ones without the ethical issues. And we get quantitative yields of our gamma valerolactone. Now I'll pass you over to my colleague Ahmad, who will speak a little more on hydrogen production.
Right. Hi. Good day. Right. So my research is in uh, pollution remediation with hydrogen production using light. Right. So we will be removing a pollutant from, in this case, water, using light via photocatalyst. So a photocatalyst is a catalyst that utilizes light to perform catalytic reactions. So as you can see in the diagram to my right, your left, right, when the light hits the catalyst, right, it forms something called an electron hole pair, where the electrons from the valence band is promoted to the conductance band, right? So the oxidation of water in the system takes place to form a hydroxyl radical, and the oxygen in the air is reduced to form superoxide. Now, these two reactive oxidizing species degrades the organic pollutant. So if you look on this side here to my left, right, you will see methyl orange, which is our model dye, model pollutant, so it's a dye. And we use the catalyst to remove the dye, and you would see here the gray solution that is the catalyst suspended in the solution. So after the dye is removed, so once the catalyst is filtered out, it will be clear and colorless. So just to touch a bit on the results. So I forgot to mention that this process also produces hydrogen as a byproduct of the degradation of the dye, of the pollutant in this case. So you can see here on the graphs to my left, you would see that in the blue line, which is the hydrogen that is being formed, the orange line is the hydrogen that is being formed, increases, while the blue line, which is the dye being degraded, is decreasing. So as the dye is decreased, the hydrogen is increasing, and as the dye has finished degraded, the hydrogen drops off. Now we wanted to see what is the importance of these reactive oxygen species in the degradation. So we performed the same degradation in an inert environment, which is nitrogen, and we saw a drop in the degradation of the dye, and we also saw a drop in the amount of hydrogen being produced in this reaction. Now, the hydrogen being produced in the nitrogen reaction is pretty much what we expect to see, right? However, in air, we are seeing a higher concentration of hydrogen being produced. Now, this is not reported on before, and more investigation needs to be done as to why we are producing more hydrogen, right? So it could be an alternative mechanism taking place as to what I had mentioned beforehand, right? So the importance of this is if we are able to remediate wastewater and produce hydrogen at the same time, that is a vital technology for our future, right? I would like to thank you for listening to my short presentation, right? Any questions, concerns, and queries, you can ask us in Q&A session after. Thank you very much.